I just wanted to show you some of the stuff I've been exploring with Kalman filters. So without going into a long diatribe about how all of this works, I'm just going to show you what's going on and then kind of talk about what I hope to gain from this level of analysis. So sort of the basic idea is you've got this inspector satellite that's 1 degree away, approximately perched plus perturbations, looking over to a target satellite. And what you're seeing represented in purple here on the inspector side and blue here on the target side is truth data. Now, STK has this software known as ODTK, or Orbit Determination Toolkit, that I'm going to show you some pretty interesting stuff in, but the first one I wanted to show you is it can do full simulated Kalman filter models. So basically, I put into ODTK this inspector satellite with its optics only sort of camera looking towards the target area. It has no other data, no onboard GNSS, no support from the ground, and we're just going to watch how the Kalman filter decays over time. Also, what you're seeing here in this sort of box is what the inspector satellite's optics are seeing. Let's just go ahead and play, and we'll kind of watch how this scenario evolves. Sorry, I forgot to mention this yellow line here is the Kalman filter estimation. So taking a snapshot from the camera of the inspector satellite, I think this one is every 60 seconds. It's trying to estimate the location of the target based on that data. And then something interesting happens right here, where it basically goes to this smooth motion. And it's going to continue for about 12 hours. And it's very easy to understand what's going on here when you look at the sensor scene. So essentially, there's no data flowing into the Kalman filter right now. The only data that it has is the last known location, and it's getting no new data points because the target is no longer optically illuminated. And then you can see this huge jump where suddenly the target comes back into the field of view of the inspector satellite because the sun has now transitioned back to solar advantage. And you can see it's going to start estimating again. And I think it's easy to say what a Kalman filter is, but until you actually model one and get to see sort of these track lines that just suddenly go smooth, and you can look down here in the optics of the camera and watch the target fade into the background noise because the sun has gone away, which happens right there. It's hard to really understand, so we're not getting any data in our sensor scene here. It's hard to really understand how Kalman filters work without seeing this. You can also see that the inspector was estimating its own location off of its original truth data for the target's location. So that's like a combination of factors there, not just the error in the target estimation, but an error in the inspector's own estimation of its location. And we can also add covariance onto this. So let's just show to a 95% probability where could this vehicle be, and you're just going to get sort of this growing cone. So right now, this is the 95% probability of the target's location. You can see it never really does not encompass the actual truth data location. It's just the error bubble grows and grows and grows. And primarily, it's always going to be pointed down the in-track vector because range will be the biggest factor to the error of the target location. Whereas you can see sort of this cross-track is a very small error estimation, and radial is relatively small as well. The depth perception limitations of the camera is what leads to this very large error bubble. You can see it's just growing because it's not getting data. It's going to shrink again as it starts to get new data, but it's still going to be a relatively much larger volume than what we started out with. Okay, let's take a look at another one. Here I've added some additional viewpoints just to kind of show how this is all working. And let's see if you can guess the orbit of this satellite and how it's Kalman filter estimating. So here you're seeing what the optics are seeing. This is basically if you had a perfect optics, what your satellite would be seeing field of view wise. And then here you're seeing the Kalman filter estimation. All right, any guesses? Of course, this is an NMC. Not exactly sun synced. That was a mislabeling on my part. You can see the sun is nowhere near over there. It's actually almost 90 degrees off there. And what I like about this is you kind of get two sort of interesting ideas from this simulation. A, you can see it's significantly better than that 1 degree away perch from before. But B, something I never really considered is there's still moments where I lose the target. And there's an interesting one that happens right about here. So you still are getting data, 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 data. And then it suddenly goes smooth. You see that? No more data. It's not estimating anymore. And it's kind of easy to see from these two screens why that's happening. So lacking these two, you might not be able to understand why did it suddenly go smooth data if you were just looking at this Kalman filter estimation. But on this side, it's very clear to see the reason why you lost data is because you are looking at the surface of the Earth right now. You're in Earth exclusion, essentially. So this is modeling very low res. Let's see if we can get any more detail out of that and see if we can actually see continents. So yeah, you can kind of now make out a little bit of grassland. This might be an ocean view right now. Let's see if we push play through, if we can actually see a continent or two. Yep, there we go. So we actually got to look at a continental pass over to an ocean line there. And that's right when the Kalman filter stopped getting good data. So kind of cool to tie an actual sensor look into, okay, but you have to remember Earth exclusion, and NMCs are not just free persistent data. And we can add the covariance to this one as well and kind of watch how the covariance sort of twists with the NMC itself. Right now it's just growing because we're not getting any data because we're in that Earth exclusion period. But the 95% probable still contains the location of the target. Now we're getting data again, and you're going to watch how the covariance bubble sort of shifts with the location of our NMC satellite. So essentially it's going to be spinning around the target. Speed up time a little bit, shrinking, growing. Let's see, we're trying to keep the target in our center field of view. There are some times where other exclusions will cause us to lose the target. And because we're not perfectly sun synced, there actually are a few times when the target just doesn't have enough illumination to be visible out of the noise floor. So you can see basically this simulated Milstar satellite I threw in here is almost completely in shadow. Maybe you're still getting some glints off of other components on the satellite, but for the most part, the vehicle got lost in the noise floor because I'm not perfectly aligned with the location of the sun. So there's the sun, and there's the satellite, and we're just not getting enough light to pull the satellite out of the noise, at least for very brief periods of the day.